Okay, good afternoon. First, as usual, a check if you can hear from home. Okay. Then you should see the screen as well. Okay. So we can start. First of all, let's see if I have it here. Just a second. Okay. So, a recap of what we saw last week. We introduced discriminative classifier logistic regression that was based on some assumption on the kind of separation rule, in particular on the separation boundary, and paired with an interpretation of the score that is associated, so the separation boundary is this equal to 0, and the value that we compute, we said it's called a score, and we gave an interpretation of the score, which is a linear, unaffine function in X, so we have a linear term and a bias. Then this represents also the boundary in the sense that W transpose X plus B is the separation plane. And we saw how we can transform these assumptions, so separation rule, scoring function, and interpretation of the scoring function into a model that we can, whose parameters we can learn in a probabilistic way. So we saw that given these assumptions, we can map a score to a class posterior probability through the sigmoid function. So W transpose X plus B, which is the score for X, corresponds to what? The sigmoid of the score is the probability of class 1, of class being 1 given X. Then we saw that we can learn the model parameters by maximizing the likelihood function over the training set, that is the probability of the classes given the samples. We have seen that this can be interpreted as minimization of the cross entropy between the model prediction and the class labels, and then the same problem can be seen as minimization of a loss, let's take this one, of a loss that depends on the sample, on the label, on the parameters. And essentially the loss is a loss that we called logistic loss, that is a function of the product score of the sample xi times its label, and as a function of this product, we saw it has a loss of this kind. Points that have a large value for the ISI are points that are correctly classified, will have an exponentially decreasing loss. Points for which this is negative are incorrectly classified, and as we move away from the separation plane, our loss will increase in a linear way. Then we said that the model that we presented has some issues in the sense that it requires enough data to avoid overfitting, and in particular it requires enough data that are misclassified to avoid overfitting. It needs to see many errors in order to be able to understand where to put correctly the separation rule. Why? We've seen, for example, that if we don't have any error in our training set, then we can make our loss arbitrarily large by tending the norm of W to infinite, which corresponds to having scores that also go to plus or minus infinite depending on the label, but that means that once I multiply them by the label, since all the points are correctly classified by these planes, also the score times the label will go to plus infinite. So all the samples will contribute a loss that will go towards 0. And having a loss 0 is the minimum because the loss is always positive. So it's not a minimum, it's a lower bound of the loss. The loss can never be lower than 0. We said that to avoid this problem, one thing that we can do is consider what happens in this simple case and see that large number of W's correspond to models that are overconfident. We have said large norm may correspond to models that are overconfident. A large norm of W means what? Means that as soon as I cross the separation boundary, my posterior probability for the corresponding class will quickly go towards 1. Now, if we have lots of data that we use for training, and we have enough errors that support the fact that this probability should go to 1 quickly, then our model will probably generalize well. But if we have few errors, as we said, this may be just an effect that the model doesn't see enough errors to actually understand that there are points from the other class also in that region. To reduce the impact of this phenomenon, we can add a term that penalizes solutions with large norm. This is called a regularization term. A regularization term penalizes models where the norm of W is large. In this way, we're trying to force the model to give us solutions with a smaller norm of W. Now, this has the effect that we will reduce typically the risk of overfitting, but of course, now we are not optimizing just our original loss, so that means we may have worse results on the training set. But these results may generalize better. Now, another thing that we didn't say, and we will say it again later when we will see why this model does not always perform well in terms of actual cost. We will see that in a moment, later tomorrow in the lab. Then we will go back on that. Is that we gave a probabilistic interpretation to the score. And our model was trained to maximize the likelihood of the training class labels. Now, how strong this interpretation of the score works depends on several things. For example, as we've seen in generative model, if we make a bad assumption on the distribution of the samples, then this may lead to models that, even if they are probabilistic models, they produce scores that are not calibrated. The actual cost is not close to the minimum. This can happen also for logistic regression model. In particular, if we have overfitting, we may end up with models that do not properly capture the dynamics of the class posterior. So if we don't regularize and we have few samples, we may end up with models that are overconfident. So even if we assume that this was the interpretation of the score, in practice, this does not reflect the class posterior probabilities of the set that we are classifying, which means that we will see, again, a miscalibration error when we evaluate the model. But also the opposite is true. If we regularize too much, we tend to lose the probabilistic interpretation because the model is not capturing the characteristics of the class labels even on the training set anymore. So even if we have lots of data, if we don't capture properly the characteristics of the data on the training set, then our probabilistic interpretation of the score becomes weaker, and in this sense, also on the test set, we may not be able to perform optimal decisions using the theoretical threshold that we have seen. Typically, we see essentially that logistic regression models are well calibrated if we don't regularize and we have lots of training data. In this case, the model, and of course, the application data is assumed to have the same characteristics as the data the model was trained on. Otherwise, we will never get, we may never expect to get well-calibrated results in any case. We may by chance, but it's not general. However, if you assume that application data and training data are similar, then as long as we have enough data and we don't regularize, we will see that the model performs well in terms of calibration. So we will see minimum cost close to the actual. Once we have few data and we need to take into account regularization, then we will see that if we don't regularize, we may have bad results in terms of mean DCF. The model is overfitting, but also the actual DCF may be worse because overfitting may introduce miscalibration errors. And if we regularize, we may improve our mean DCF because we improve the model generalization, but we may see that our actual costs may become even worse, because once we regularize, we essentially change the position of the optimal thresholds for different applications. Now, if our model was, as we said, trained for a specific application directly, then this will not. So if we use a prior weighted version of the model where we train for a specific application, then we will not see this phenomenon. But if we use a general model, as we have said, because we don't know the application in advance, and then we simply want to adapt to the application, as we have said, by transforming the log likelihood ratio score, the logistic regression scores into a log likelihood ratio, and then using the theoretical threshold that corresponds to the application, we see that this may fail when we are regularizing strongly the model. We see at the end of the course a way to deal with this phenomenon that will be based on the logistic regression model, trained in a way that will typically not require regularization, and we will see that this allows us to actually produce scores that are well calibrated, and we see how to use this tool to also calibrate the scores of different models like the generative ones. But for the moment, know that when you will train this on the project data, you may typically see that once you regularize, your minimum costs may improve, especially for the more complex model, the quadratic version of the logistic regression that we saw last time. You may see models that improve in terms of minimum DCF, but get much worse in terms of actual DCF. And this is something that is explained by this phenomenon. The more we regularize, the less we preserve the original probabilistic interpretation of the score. Now, we have seen also last time how to extend the logistic regression to account for different priors than the training set priors, and how to extend the model to perform nonlinear classification. We've seen a way to perform nonlinear classification by doing what? Essentially, we saw that, for example, if we want quadratic separation surfaces, we can cast the problem as a linear model that employs a transformed version of our features. What does it mean? It means that we can cast a nonlinear classifier as a linear classifier with non-linearly transformed feature vectors. This is not necessarily the only approach. We can also imagine that we directly work with the scoring function, make the scoring function parametric, a generic parametric scoring function. We will not see this approach to this year. But the approach, a possible approach that we will see also today consists in taking our features, making a feature expansion, and then training a linear classifier with the expanded features. We've seen that this corresponds to nonlinear separation rules. Nonlinear separation rule that correspond to linear separation in the original space. Now, and of course, then we also saw last time, but for today we will not need it, but we also saw how to extend the logistic regression to multi-class problems. Other questions on this part? Okay, then what we see today is an alternative approach that works for binary problem. In this case, the extension to nonlinear, to multi-class is non-trivial, and we will actually say that there are a few possibilities, but in practice we will not use the model for multi-class tasks. But for binary, it will be a model that allows to perform nonlinear classification using this approach with one advantage. Here we said last time that if you want to apply this approach, it's expensive because the expansion may be large dimensional. We said, for example, that if you want our scoring function to be a degree D polynomial in X, then the equivalent expansion would be of size the original feature space to the power of the degree. So if, for example, we have 10 input features, then a degree for polynomial will have an expansion that is 10,000 features. And if you want more complex surfaces, this grows exponentially quickly, so it becomes unfeasible in practice. So we can't afford to compute this expansion. The method that we will see today, allows to do this without actually going through the expansion. How, we will see today. Okay. Before we see how to actually achieve this linear expansion, let's first start to see the model. The model is called super vector machine. Let's see what is the model and how it behaves and what is the goal of the model for a linear task. So we consider again a binary problem, and we go back to the simple problem of finding a linear separation rule between the classes. We've seen logistic regression as a way to do that, to find a linear separation rule where the linear function has a specific interpretation. It's the score that corresponds to the ratio between the logarithm of the ratio between class posterior probabilities. Now we see that with this model we forget about probabilities, so we will introduce the model in a way that is tied to geometrical reasoning. So the model will not have a probabilistic interpretation. Then we will see what are the issues of this. But we will see a different approach to find a linear separation rule with a different criterion, and then we will see how this allows us to extend the model to nonlinear classification. Now let's go back to the problem that logistic regression was not able to solve without adding a regularization term. The simplest problem that we can think is we have two classes, we have the set points of the points of two classes, and we assume that these classes are linearly separable. What does it mean they are linearly separable? It means that we know that there is a hyperplane that correctly classifies all the training set points. Of course, we always talk about the training set here. Let's just see if I forgot something. No. So this is the case here. If these are the training points, we have there are hyperplanes that perfectly classify the points. Let's assume the red class is class +1, as usual, +1 and -1. We use the labeling that we use for the lost version of the logistic regression. So we have class true is +1, the other class is not 0, but it's called -1. We use the ZI version of the label that is +1, -1. We have, in this case, hyperplanes that separate the classes, and typically when this happens, except if you are very unlucky with your data, you need to construct them for this to happen. If you have one linear separation rule, typically you have an infinite number of separation rules that also work. Now, problem, here I have a task where I will do what? Well, of course, it makes sense to select a separation rule, one rule that classifies correctly the training set. The training set can be correctly classified. So let's try to focus on solutions that do things correctly on the training set. But we want also these solutions to be robust for unseen data. So which kind of solutions should I choose? Here I have several options. For example, I have this option. Let's call it 1. Then I have this option. Let's call it 2. Then I have this option. Let's call it 3. Which one among these three would you choose? Let me draw this one a bit better. which one would you choose and why? So who would choose 1? Who would choose 2? Who would choose 3? Okay, now why would you choose 3? What does it mean more evenly? So why wouldn't you would not choose 1? What is bad about 1? Okay, now forget about the prior. Imagine that we want to find a separation rule. We said we are not working with probabilities here, because we will see that the criteria that we use has nothing to do with probability, which will cause problems in selecting the threshold later, but we will solve that later once. Now, just geometry. You know that you have to choose one of these 3, and the application, you know that you will use this, regardless, you will not change it or shift it or do anything. You have to choose one, and this will be the separation rule that you will use for the application. And ignore the error, the cost of the errors, assume that the cost of errors are the same, the priors for the 2 classes are the same, so the easiest model where there is no differences in the 2 classes. So it's not, ignore the problems like I have more errors of 1 class, but I want to avoid that. That is not the case. Here, we assume that all the 2 classes have the same cost, the same probability of appearing, and so on. Then this is not true in practice, but we will see how to deal with it later. So why is 3 better than 1? Yes? Yes, the problem is that with 1, I have points that are close to the separation rule. These are training set points. I can imagine that application points behave similar to the training set points, but not exactly the same. So there will be, if I have 1 training set point, I imagine that in my application, I will see something around that. Now, if I have points that are close to the separation rule, there is a high chance that this application point will then fall on the wrong side of the plane. If I select something like 3, you see here I was drawing my points. The way I was drawing, I didn't even pay attention to that, but none of the points ended up in the wrong space. So there is lower chance than the points end up in the on the wrong side. Of course, here we assume that the way the points are, the application points are spread around is similar in all directions, and they are spread around the training points. So the training points are representative of application points. But apart from this, and we will not do any assumption actually on the distribution in reality, but we can imagine that if the behavior of the samples along the different directions is the same, then having a plane that is far from the training set points will ensure that there is lower probability that a test sample will fall in the wrong space. That means that if I have a large space between the separation rule and the actual training set points, there is a lower chance that I will make an error on unseen data. So intuitively, we are saying that if there is a large gap between the training set and the separation rule, the model will probably generalize better to the test set. There is lower probability that I will have an error for the evaluation set, which means that the model should generalize better. Of course, it will depend on the specific data set. This is not something that holds every time. It's something that makes sense in general, but I can always construct you a data set where this does not work. But in general, we can imagine, by the intuition, we can say that in general, if we don't know anything about the data, then having a large separation between the two classes leads probably to a model that does less errors on data that it has never seen. So this we already said before the lecture. So a good way, we may decide that a good way to select a hyperplane when our classes are linearly separable is to select an hyperplane that among all those that don't do any error on the training set will also have a larger generalization than the others, which means a hyperplane for which the training set points are farther away from the separation surface. Farther away from the separation surface means that the area, this area here, that is the area between two surfaces that touch the point and are parallel to the separation rule, and the separation rule itself is large. So there is a large gap between the two classes. If this is W, there is a large gap between the two classes along the direction W. Now this gap, this region here, is also called margin because it represents the margin that there is between the two classes if I choose that W as separation rule. The margin is defined, here you have the proper definition, as the distance of the closest point with respect to the separation hyperplane. So actually the margin is defined as this distance, but it doesn't really matter for how we use it, whether you call margin the whole area or just this area, it doesn't matter. Sometimes you find the margin defined as margin for the red points is this one, margin for the blue points is this one. So you have two different margins for the two classes. Again, that doesn't really make a difference because if you use this interpretation, you will in any case end up that optimal solutions will have these two distances that are equal. So the two margins will again be just one. And if they are equal, if you talk about the margin or twice the margin, it doesn't really change. So sometimes I may improperly say the margin and say all this region, but the definition is just this distance. But as I said, all these concepts are essentially the same thing. We want a large margin, a large separation between the classes, or, which is the same, a large distance of the closest point of the training set from the separation rule. So having a large distance of the points from the separation rule means that we will have a large margin, which means that our model will probably generalize better to unseen data. Problem, we now need to figure out how to find the solution with largest margin. So we need to find a way to avoid flies coming in your mouth. Okay, you will need to find a way to transform the intuition that we said we want a large margin into an objective function that takes the training data and by optimizing some objective that will represent the margin will give us the solution for W. For that, we need to be able to represent the margin. Now, to represent the margin, we need to start. I will draw again the task with the definition of the distance of the closest point from the separation rule. The separation rule, as usual, is W transpose X plus B equal to 0. So we have parameter W that represents the direction, a bias B that controls essentially which among the different planes I will select. When I have this is equal to 0, that corresponds to our separation surface. So for example, this one. Now, I need to find, if I want to find the separation surface that has the lowest the largest distance from all the training points and still correctly classifies all points, of course, I first need to define how I measure the distance of a point from the separation surface. The distance of a point from the separation surface can be computed in this way. Essentially, we project our point on the separation rule, and then the absolute value scaled by the norm of W corresponds to the distance, which makes sense. Points that are for which this is 0 will have indeed a distance from the separation rule that is 0. Then as I move further away, this distance will be obtained how? Projecting W over X over W and adding B will be 0 for the points that are here. For the points that are farther, it will move the projection along the direction W. I need to normalize, because if I want this to represent a distance, then the projection direction should be normalized. So I need to renormalize by the norm of W. So this is the way I can compute the distance. And of course, I need to take absolute value because these are distances. So the size I am with respect to the separation rule doesn't matter. A distance is always positive. For blue points, the distance is positive. This is not a score. This is a distance, so it's always positive. This is how you compute the distance of a point from the separation rule. And what we want to do is find planes that correctly classify all samples and have the lowest distance. Now, how can we define that a hyperplane correctly classifies all samples? Well, for a plane that to correctly classify all samples, it needs to satisfy these constraints. This is, we call it F, but it's the same thing as the score of the logistic regression model. We will call it S later on, because this will be the SVM score. When this is 0, we have a point that is on the surface. When this is positive, we have a point that is in the class 1 space. When this is negative, we have a point that is in the blue class space on the other side of the separation rule. This is the same as with logistic regression. We also saw in logistic regression. Positive score, I'm on one side of the plane. Negative score, I'm on the other side. So if a hyperplane correctly classifies all samples, it means that the score will be positive for sample of class true and will need to be negative for samples of class false. That is class Zi equal plus 1, Zi equal minus 1, which I can compactly say that Zi, let's use F, or I will use S later on, must always be greater than 0. The score times the label must be positive for all the points to be correctly classified. We said this already in logistic regression. Points that are correctly classified are points in which the score is positive and the label is positive, so the product is positive, or the score is negative and the label is negative, so the product is again positive. If the score is positive and the label is negative, then that's an error. If the score is negative and the label is positive, that's also an error. So when this is greater than 0, then the point is correctly classified. When this is lower than 0, then I have an error. So for all the points to be correctly classified, it must hold this. Or if I rewrite it explicitly in terms of W and Xi, this must be true for all the samples. So we can represent our problem as what? Well, we have the distance. The distance for point Xi is computed like this, but here I can replace, here there is one step more. Let's remove this. I can represent it in this way. This is just F, the F we have before. We said F, which we also call score because it's the same function. It's W transpose Xi plus B. So this is the definition of distance, absolute value of this. Which means that our goal is to do what? Find the hyperplane whose minimum distance is maximized. So we need to find among all hyperplanes the one that has the maximum margin. How I can define the margin? The margin is the minimum of the distances, minimum over the samples of the distance. Or if I replace with what is written there, absolute value of the transpose xi plus b. This, if I run this I over the training set, is the minimum distance of all the points in the training set from the separation rule. This is the distance of point xi. The minimum over I of the distances of the points xi is the minimum distance of a point from the separation rule. Do we agree? Or not? Distance of a point, I want the minimum distance of all the points from the separation rule, so I take minimum. This is given W. If I give you a W and a B, this expression tells me what is the distance of the closest point to that separation rule, separation surface. I want the separation surface which has maximum distance. So what I want is to find W and B for which this distance is maximum. Actually, argmax because I want W and B and not the value of the distance. Max gives me the value, argmax gives me the values that maximize the function. Margin for a solution W and B, which is the minimum of the distance over all the samples, I want the maximum margin solution, W and B, that maximize this minimum distance. And I want that my model classifies correctly all the samples. So this is a maximum, that is a constrained maximum, it's maximum subject to this holding for all the samples. So the maximum distance among hyperplane that correctly classify the samples. Why do I need to add the constraint? Because without the constraint, it's easier to make a large margin classifier. If I have these samples and I put my separation rule here, I have a large distance from all the points. But it is pretty useless because one of the classes will always be incorrectly classified. So I need to ask that the model correctly classifies all samples, and among these constraints, I'm finding the maximum of the minimum distance. Now, you can imagine that working directly with this expression is not nice. We have W, we have a maximum of a minimum, we have constraints, we have W in a fraction where we have on the numerator W, on the denominator the norm of W, which itself is the square root of the sum of the squares of the elements of W. So working with this expression is not very straightforward. So what we will do is we will cast the problem in a different ways that essentially provides us with a way to express the same problem, so to find the same solution, but with a problem that is much easier to work with. Now, we'll try to give an intuition, and I don't know how it will come, but it's not in the slides, but I will try to give you an intuition of the solution that we will find, what it represents intuitively, by considering what happens if we consider a model, how we can intuitively derive a solution, an equivalence problem that we will see then, we will derive it formally, by considering this problem. Let's imagine I have a hyperplane W, a set of W's, and B that classifies my samples. Now, I can represent the same separation rule in an infinite number of ways. I have this W, but if I take 2 times W and 2 times B, I get the same solution, okay? This represents, geometrically, they represent the same hyperplane. Do we agree? So when I'm thinking about a separation rule, essentially, what do I have? If I think about a separation rule, the same separation rule can be represented by an infinite number of planes. I can, among this infinite number of planes, decide to select one. Which one? We select the one, and for the moment we consider only planes that correctly classify the samples. We consider only those planes for which, well, the closest point, so the closest point to the plane has a distance equal to plus or minus 1, depending whether it's a blue or a red point. Not a distance, a score. So we have W. We can represent the same surface with an infinite number of planes. We will select one for which this holds. If the closest point is from the red class, then that will have a score of 1. If the closest point is a blue point, then for that point, this will hold. And in any case, what does it mean? That for all the points, W transpose X plus B will be what? Will be greater than 1 if the class is plus 1, and will be lower than minus 1 if the class is minus 1. If I want that the closest point is a distance that is plus 1 if it's red or minus 1 if it's blue, it means that all the other red points will have, I need to put equal as well, a distance that is at least 1 if they are red, and at least minus 1 if they are blue. That means that essentially we represent the margin by a region that is defined by the solution of these two equations, W transpose X plus B equal 1 and W transpose X plus B equal minus 1. Among all the possible solutions, we consider only those where the margin can be defined in this way, okay? So we consider only, since for any plane we can find an infinite number of solutions, we will restrict to consider only solutions for which this holds. But if we restrict solutions for which this holds, we can see that the range of this area will be proportional to the norm of W. If we have a large norm of W, again, take two planes. If the norm of W is large, then the solution Wx transpose plus B will happen where? Well, let's not draw. Let me draw just the plane. Norm of W is very large. W transpose X plus B equal plus 1 will happen where? Remember that the separation rule is W transpose X plus B equals 0. If the norm of W is very large, then X needs to change a bit for this value to become 1. So essentially, it will consist of points that are close to the original surface. If the norm of W is very small, to achieve the same value, I will need to have points that are far from the separation rule. So it means that if we define the boundary associated to an hyperplane W as the set of points for which W transpose X, the score is 1 or minus 1, then the larger the norm of W, the smaller this region. But if we restrict ourselves to look, well, the larger the norm of W, the smaller this region. So we can say that to have a large margin, we want a low norm of W. A low norm of W, or let's work not with the norm of W, but with this square, and a low squared norm of W corresponds to a low norm of W. So if we have a low norm of W, we will have a large margin. A large margin, this needs to be a margin, so it needs that for this to represent correctly a margin, for all points, we need this to hold. Notice that this expression can be, these two expressions for the two classes can be written in compact form in this way. For all classes, zi times the score must be greater than 1. Does it work? Yes. If zi is 1, so the points is from class 1, this becomes W transpose xi plus b greater or equal than 1. If zi is minus 1, I have minus 1 here. I multiply everything by minus 1, so I change the sign of both sides, and I need to change also the direction of the inequality. I have W transpose xi plus b lower or equal than minus 1. So this is a compact way to express both constraints. So I can require that the margin is large by asking that I have a small norm of W subject to the fact that all the points must be outside of the margin. The margin is defined by the region W transpose xi plus b equal 1 on one side and W transpose xi plus b equal to minus 1 on the other side. All points must be outside of the margin region, and we know that this region is larger if the norm of W is smaller. So asking for a small norm of W will give me a solution that has a large margin subject to all the points being outside of the margin region. Now, this is one possible way of deriving it. If you don't like the intuitive way, we can see formally that we can recover exactly the same expression by modifying our original problem. Our original problem was this minimization of the maximization of the minimum of the distance of each point from the hyperplane. Now, subject to all points must be correctly classified. Now, the first modification that I do is I add a zi term here. Why I can do that? Zi is plus 1 or minus 1. I'm taking an absolute value here. So if I multiply what's inside by a negative value, it doesn't change. If I have absolute value of x is equal to absolute values of minus x. So I can multiply by minus 1, and I will get the same value. And when zi is 1, I'm not changing what's inside, so I still get the same value. So the problem can be equivalently written in this way. Now, as we said before, no, okay, we need one more step before what we said before. Now, the first step that we do is we see how to throw away the absolute value. Absolute value is by itself already something bad. Well, it turns out that we can directly throw away the absolute value, because if we throw away directly the absolute value, we will not have the same problem anymore, but we will have an equivalent problem that has the same solution. That is, a solution that is optimal for this problem will also be optimal for the previous one, and vice versa. Why is that? We can show that the solution the problem are equivalent thanks to the fact that the classes are linearly separable. If the classes are linearly separable, there exists W and B which correctly separates the classes, which means that for those W and B, zi W transpose xi plus B will always be positive, which means that also the minimum of the distance will be positive. So there is a solution of this problem where all these terms are positive. Now, let's imagine we have a hyperplane that does not, and we can drop the constraint. So we look for the minimizer of this. Now, and this allows us to also drop this constraint. Why? Let's imagine a hyperplane that here I don't have a constraint problem anymore, so I removed my constraints. But let's imagine I have a hyperplane that does not correctly classify the points. Then the minimum of zi W transpose xi plus b will be lower than 0 from that hyperplane, which since we are maximizing here with respect to W and B, and we know that there is a solution which has a positive minimum distance, this problem will never, by default, be able to select a solution which does not correctly classify the samples. I don't need to enforce the constraint because I know that solution that correctly classifies all samples will have this value that is positive. Solution that misclassify at least one sample will have this value that is now negative because one of the points will have a negative Zi, Si. And I know there exists at least one correctly classifying hyperplane, so I know that all planes that do not correctly classify my samples cannot be the optimal solution of this problem because they would give me a negative objective while I know that there exist W's that provide a positive value for the objective function. So the values that give me a negative objective function cannot be maximizer of the objective function. And vice versa, if we restrict, so all points that were not admissible in the first problem are not solutions of the second problem. And then for all points that were admissible solutions of the first problem, so they met the constraint, since this term is always positive, then for those terms the objective function is the same because the absolute value of the positive number is the number itself. So if I throw away the absolute value for those W's and B which correctly classify the samples, the objective function is still the same. I'm not changing the objective function. So I have an objective function that now allows me for solutions that do not classify correctly the samples, but those will result in a lower value of the objective, so they will be thrown away by the maximization. This allows me to throw away the constraint that all the samples must be correctly classified. The constraints will come back again. Now, I have a minimum here over the samples. This term on the numerator depends on the sample, but the denominator does not depend on the sample. So what decides the minimum is the numerator. So I can bring this W outside of the minimum. The minimum of, let's imagine you have x1, x2, x3 divided by a constant. The minimum of these three will be what? Will be the minimum between x1, x2, and x3, the result divided by the constant k. So I can bring the norm of W outside. Now, again, this still doesn't give us an easy to solve problem because I have a minimum here and a maximum outside. So now we introduce the observation that I was doing before. The objective function is invariant to rescaling of the parameters. What does it mean? It means that if we find a solution W and B that maximize this expression, then also alpha W and alpha B with alpha positive, because I don't want to flip the direction of W, and also alpha must be different from 0, otherwise it will not be true anymore, because I will have a division by 0 here essentially. If alpha is positive, then this will also be an optimal solution. How can I see it? Well, let's imagine that W gives me the optimal solution for this. Now, if I multiply W by alpha and B by alpha, I get the die W transpose Xi plus B. These terms are multiplied by alpha. The minimum over I, and then outside I have 1 over alpha W. Now, this alpha, I can bring it outside as well because I can collect the alpha. Here I can write it as alpha Zi W transpose Xi plus B. Then I have minimum over I of this, as before. I can bring the alpha outside. I can bring alpha outside of this norm because the norm of alpha W is alpha times the norm of W. And then these two alphas will just simplify. So if I have a solution W and B, the objective function that I have is the same value as for the solution alpha W and alpha B. So actually this objective does not have a unique minimum, but has at least an infinite number of equivalent maximum, but it has at least an infinite number of equivalent maximum. As we said before, the same separation rule can be represented by vectors W which have different norm. This is exactly what this is saying. If we change the norm of W, but we don't change its orientation, and of course we need to rescale the bias by the same amount, we're not really changing the separation rule. The distance of the points from this hyperplane will be the same, because these represent the same surface. Remember that the surface is, geometrically, the surface is defined by this equation. So the distance of the points from this surface does not depend on the norm of W, because those W's represent the same hyperplane. Which means that we can choose the value of alpha. So we have that given a solution W and B, then also alpha W and alpha B will give me the same value of the objective function. So if W and B are optimal, also alpha W and alpha B are optimal. So when we consider one hyperplane, rather than considering, we are essentially jointly considering the family of all hyperplanes that are described by vectors that are parallel to that one. We can restrict ourselves to consider only one of these solutions. Which one? Well, we can decide that we will consider only the solutions whose scaling is such that this value, the minimum of the distance of the points from the separation rule, will be exactly equal to 1. So, since we are free to select a scaling for W's because we have an infinite number of equivalent W's, we choose that the scaling should be such that the samples of each point will be in a way that the point that is closest to the separation rule will have a value zi times the score that is equal to +1. So the minimum of, this is not the distance anymore because it doesn't have the absolute value, but if it's a red point, it will have a score W transpose xi plus B equal to 1. If it's from the closest is from the blue point, W transpose xi plus B will be -1. The minimum of zi times this term will be equal to 1. And we are considering hyperplane of this kind. So we restrict our solutions to solutions in which all the points are such that points from the red class have a score that is at least +1 or more, and score of the blue class have a score, and points of the blue class have a score that is at least -1 or less. We can select W freely. That's what we were doing intuitively before. Here we are doing it formally. We are free to select a scaling for W. We select the scaling for W that corresponds to all the samples of the red class being at least at a value of the score 1 or greater, and the score for the blue class -1 or lower. And in particular, we encode it in this way for the moment, then we will show that it's equivalent to what I said. We ask that the minimum over all samples of zi times the score is equal to 1, which implies, if the minimum of zi times the score is 1, it implies that for all the samples, zi times the score will be at least 1. If this is the minimum of all the points, this is also implied. Notice that the opposite is not necessarily true. I can have values where this holds, but if this holds strict, then the minimum is not 1 anymore. But if the minimum is 1, then these equalities will hold true for all the points. So there is an implication that goes in this way. So we can represent our problem how? Well, we had to minimize, we had to maximize 1 over the norm of W times this term. But we said, let's focus only on problems for which this term is equal to 1. We said this doesn't change the solution in the sense that it will change the solution that we will find because we are restricting ourselves to finding a specific solution among a set of infinite equivalent ones, but the other ones would be equivalent. So we are not losing anything from the point of view of what we are representing geometrically by adding this constraint. If we add this constraint, then it's clear that now, if we solve the problem under with constraint, we can remove this term from the objective function. All solutions that are feasible for the problem, so all solutions that respect the constraint, will have a value of mean of Z I W transpose Xi plus B that is equal to 1. That's the constraint. So in the objective function, I can remove that term because for feasible solution, that term will be exactly 1. Which means that now I have maximization of 1 over the norm of W subject to this constraint. Now we said that this constraint also implies that Zi W transpose Xi plus B is greater than 1, so I can additionally add these constraints for any point. If I add constraints that are implied by the previous one, I'm not changing my problem. Every solution that was meeting the first constraint will also meet the other ones. So I can freely add constraints that are always satisfied by the first one, and I'm not restricting my problem. So optimal solutions of the new problem will be optimal solutions of the problem with just this constraint. If we have just this constraint, or we have both, we have the same problem, because any problem that satisfies the first will also automatically satisfy the second. Now, I say first and second, but there is a pair of constraints for each point. Which leads us to this expression. We need to maximize the 1 over the norm of W subject to the fact that the minimum of all the Zi times the score is equal to 1, and all Zi times the score is greater or equal than 1. Now, maximizing 1 over the norm is not nice from the point of view of taking gradients and derivatives. We can observe that argmax of 1 over W corresponds to the argmin of norm of W. If I have a solution that maximizes 1 over the norm of W, it will also it will need to be a minimum of the norm of W for 1 over the norm of W to be maximum. And then a model which has a minimum value of the norm will also have a minimum value for the squared norm. So argmax of 1 over norm of W corresponds to argmin of norm of W, and corresponds to argmin of norm of W to the square. Then we put 1/2 because when we take derivatives of a square, the 2 will compensate with the 1/2, so it will go away. So we can show that the same problem can be represented in this way, minimizing the squared norm of W subject to these constraints. This is the same that we said intuitively before. We said large norm of W means that the boundary where the W transpose Xi plus B is equal to +1 or -1 becomes smaller. Small norm of W, this region becomes larger. Large norm of W, this region becomes smaller. So minimizing the square norm of W will give us a large region. This minimization must be subject to the fact that all the points are correctly classified and outside of the margin, which is encoded by this and is encoded also by these expressions. Now the last step that we need to do is to throw away this minimum that we said we didn't like at the beginning and it's still there. We can actually show that an optimal solution of this problem is also obtained by simply removing the last constraint. introduced these constraints by saying that they were implied by the last one, but once we minimize the norm of W, we can show that if a solution meets all these constraints, then for it to be optimal, it will also need to meet the last one. This is also true only for optimal solution. Minimizers of this problem without the mean constraints are minimizers of the original problem. Why? Because we said the second constraint implies the first, so any minimizer of the first will also meet the second constraint. Now we need to verify that if we remove the constraint, we are not introducing new solutions which would violate this one and have a better norm. But this is not possible. Why? Because let's imagine we have two options. Either all these constraints must be satisfied. So either there is at least one point such that Zi W transpose Xi plus B is exactly equal to 1, and then that means that the minimum over I of this is equal to 1, so the problem becomes again equivalent, or this point does not exist. But if this point does not exist, it means that for all samples, Zi W transpose Xi plus B is greater than 1, strictly greater. So let's imagine that the minimum of this over I is not 1, but it's a value psi that is greater than 1. That means that now let's imagine W and B is an optimal solution of this problem. Now, if W and B is an optimal solution of this problem, which does not respect these minimum constraints, then W and B is an optimal solution for which there exists a point Xi for which the minimum over Xi of these terms will be strictly greater than 1, will be equal to psi. But now take a new solution W prime and B prime that is obtained by taking W and B divided by psi. This is a new solution. For this solution, the minimum of these terms will be equal to 1, because when I put the minimum of Zi W transpose over psi Xi plus B over psi, now this will be 1, because without the psi, the minimum would be psi. When I scale everything by psi, the minimum will also be scaled and be 1. But now, the norm of W over psi square will be lower than the norm of W. So the norm of W prime will be smaller than the norm of W, which means that W is not optimal. But our assumption was that W was an optimal solution for which the constraint was not met. This shows that there cannot exist a solution W which is optimal for this problem for which this constraint doesn't hold. If all these constraints are satisfied and W is optimal, then the closest point to the separation rule will have a value Zi W transpose Xi that is equal to plus 1. So we can drop this constraint because this constraint will be automatically selected by the model. Geometrically, what's going on? Imagine that I have a solution for which, let's remove this constraint, for which this holds, but let's say that this holds strictly. So for all points, they are more than 1. It means that the region, the margin region, would be this one, W transpose X plus B. But this cannot be an optimal solution because I can always enlarge this margin to reach the points of two classes. Which means that I can find a solution which has a larger margin, a larger separation between these boundaries, which will correspond to a lower norm. So a maximum margin solution will always touch the points of one class. If it always touches the points of one class and they are correctly classified, it means that this will always be true. So as long as it's an optimal margin solution and all the points are outside of the margin, then at least one point will be exactly on the margin region. and we can drop this constraint because an optimal solution of the problem will be optimal for the original maximum margin problem. This gives us the final expression of the problem that we will solve. That is, the maximum margin solution for linearly separable classes can be obtained by solving this constraint optimization problem, minimize the square norm of W, subject to the constraint that for all points, the score of the points times the label must be greater or equal than 1. Notice that this is stronger than requiring that the W correctly classify the points. Solutions that correctly classify the points will have this. Here I'm requiring that there is a margin between the points. So it means that I don't want the points to be just on the right side, but I want that there is a margin that is the region of space between the hyperplane and the points that is large. So the points must be all outside of the margin, and the margin is proportional to the inverse of the square norm of W. So lower norm means larger margin. So we find among solutions for which all the points are outside of the margin, the solution which has higher margin, that is lowest square norm of W. Now this is called also a convex quadratic programming problem. It's a optimization problem where the objective function is convex. Convex function is square, so it's convex. And the constraints form a convex set. So a convex set is something that doesn't contain holes. So for example, this is a convex region in space. This would be a non-convex region in space. If I take 2 points and I connect them, I have something that falls outside. These kind of problems, we have tools that allow us to solve them, and we have tools that allow us to solve them efficiently, well, sort of efficiently, in different ways. Now we'll see a first way to address this problem that will lead us to a different representation of the same problem, and then we'll see how this allows us to extend the model to linear classification, and then we will see a different way to solve this problem in a way that will make the problem look very similar to the logistic regression task. Let's make 10 minutes break here, then we resume. For the moment, we don't consider that. Later I will answer this. Okay, let's start again. Okay, we have seen how to cast our our SVM problem. This is the problem that we will now need to solve. Now, this is a constraint problem. Solving constraint problems is typically not that straightforward. We have constraints that are inequality constraints that define essentially a region in space where our feasible solutions lie, and we need to find a minimum inside this feasible solution space. One possible way to find a solution of constraint minimization problems is through a mathematical tool that is called Lagrange multipliers. Now, I will not explain Lagrange multipliers because they would take us quite some time. If you want, you have a nice intuitive explanation, which is not rigorous, but it's rigorous enough and intuitive enough to be understandable on the Bishop book. That is one of the two books that are the reference books for the course. There is an explanation that I think is easy enough to understand, that explains why Lagrange multipliers allow us to solve constrained minimization problems. What we will do is we will take this for granted and just see what is the result. Essentially, the Lagrange multiplier approach tells us that we can construct what is called Lagrangian formulation of the problem. That is a problem obtained by taking the original objective function, and then for each constraint we need to add a term that corresponds to what? The constraint, rewritten in the form, remember that the constraint was zi w transpose xi plus b greater or equal to 1. In a normalized form, this will be written as zi w transpose xi plus b minus 1 greater or equal than 0. Normal form means that on one side I have 0. So for each constraint, I will take this constraint. I introduce a new set of variables, one per each constraint, that is called a Lagrange multiplier, and then each constraint is multiplied by the corresponding Lagrange multiplier, and I need to add all the constraints, and then subtract the result from the original objective function. This is the definition, for us, it's a definition of the Lagrangian formulation. Original objective, and then we introduce one value, alpha I, one multiplier for each constraint, and we build this new function where the original objective is extended with the sum of the Lagrange multipliers, each multiplied by a term that represents the one of the constraints of our original problem. Again, if you want to know why this is a good approach and why this works, Bishop book. We can use this expression to solve the problems in two ways. We can use this expression to solve the problems by, first of all, an optimal solution can be obtained by minimizing the Lagrangian with respect to W and B, while we require that the derivatives of the Lagrangian with respect to alpha either goes to 0 or the corresponding Lagrange multiplier alpha I is equal to 0 itself. Again, why Bishop book? Now, the problem being convex means that we can also solve the problem in an equivalent way, maximize this Lagrangian with respect to the alpha I, subject to the fact that the derivatives of the Lagrangian with respect to W and B are 0. And of course, this I didn't say, the Lagrange multiplier must be greater or equal than 0. So this Lagrange multiplier is assumed to be greater or equal than 0. What does it mean? It means, let's look at the second way to solve the problem. We can find an optimal solution by maximizing this Lagrangian with respect to the alpha, to the Lagrange multipliers, while requiring that the derivatives with respect to W and B are 0. Let's take the derivative of the Lagrangian with respect to W and B. These are the expressions that we would obtain. For the derivatives to vanish, we need that W is equal to the sum over I of alpha I z I xi. What are these? Xi is the ith sample with associated label Zi, and alpha I is the corresponding Lagrange multiplier. This means that for an optimal solution, for a solution to be optimal, we can maximize the Lagrangian with respect to alphas, and then once we have found an optimal solution in terms of alphas, the optimal hyperplane W can be expressed in this way. So an optimal plane W can be expressed as a linear combination of the training set samples. Xi are the training set samples. Zi's are labels, and alpha i's are values, are scalar values. This tells us that an optimal SVM solution, already says something, an optimal SVM solution can be expressed as a linear combination of the training set samples. And then we have a second constraint that derives from the fact that the Lagrangian must be, we must take a zero gradient, a zero derivative value of the Lagrangian with respect to the bias term B. Now, if we take this and replace this expression inside the Lagrangian, what we obtain is a function that now depends only on alpha and does not depend explicitly on W. And we said that the optimal solution is maximizing the Lagrangian with respect to alpha. So we can find the solution in terms of alpha by maximizing this expression. This expression is obtained by taking the Lagrangian formulation and replacing W equal this. If you replace this W inside this expression and you do all the manipulations, remembering that W square norm of W is equal to W transpose W, so you have all cross terms here, what you obtain is an expression that looks like this. We need to maximize the Lagrangian. We have that the maximization is still constrained. In this case, we have the constraint that all the alpha i's must be greater than zero, greater or equal than zero. That's because they are Lagrange multiplier. And we need to add an additional constraint that is, we need to maximize the Lagrangian subject to the fact that the derivatives with respect to W and B are zero. The derivative with respect to W is zero. We already incorporated it directly by replacing the value of W with the value of W expressed in terms of alpha. We still need to force that the derivative of B with respect to B of the Lagrangian is zero. So we need to add the constraint that the sum of alpha I z I is equal to zero, which we will see when we do the laboratory. Is a term that creates several problems in training. It's a term that we will see how to throw away because it makes training more difficult. But the SVM formulation can be expressed in this way. So we can find W how? Solving this additional problem subject to alpha I is greater or equal than zero, and the sum of alpha I z I is equal to zero. These alpha I are called Lagrange multipliers. Once I have found an optimal solution of this problem, I can obtain an optimal solution in terms of W, which gives me the hyperplane that I was looking for. Now, we can also express this objective function in matrix form in this way. If we collect all the Lagrange multipliers in a vector alpha, this is a quadratic objective in alpha, where the matrix H that represents the quadratic form is composed of terms of this kind. The term in position ij correspond to zi, zj, xi transpose xj. These are two samples in the training set. Now, for the moment, it may look like a more complex way of solving the original problem because we have to go through something that is still a convex problem, but this time we still have constraints. And then once we solve this, we still need to go back and find the original solution. And then the complexity is what? W has the same dimensionality as the input space. Let's imagine that your training set consists of n samples of d dimensions. Then vector alpha has a size that is proportional to the number of samples. Remember that we had one constraint per sample. One constraint per sample, which means one Lagrange multiplier per constraint. So we have one Lagrange multiplier associated to each sample. And we see it also here. To each sample, we associate the corresponding Lagrange multiplier. However, the fact that this H depends only on dot products between training set points will be exactly what allows us to achieve an efficient way to obtain nonlinear separation rules that will be much more general than the ones that we have seen just with the quadratic logistic regression. So for the moment, it may look like a difficult way of solving the problem, but this property will be the key to extending the model to nonlinear classification. Now a couple of words on the dual and primal objective. This objective function is called dual formulation, or dual objective if I refer to the objective function itself. This is called primal formulation. That's because this is the original formulation of the SVM, while this is a formulation given in terms of Lagrange multiplier, which are also called dual variables. Now we have that for an optimal solution, this holds. In general, if we have a vector W and a set of values alpha, W and B, then for any value of alpha, the dual problem will have a solution that is lower or equal than that of a corresponding primal problem. And so the primal objective is this one. And if we have a pair of optimal solutions, then the dual problem will have the same value as the primal. So we have that in general, if we have a set of alpha that is non-optimal, then the dual objective will be lower than the primal objective for the corresponding W. If a solution is optimal in alpha and is optimal also in W, that means that the two objectives will become the same. Which means that when we solve in terms of alpha, we can always compute the corresponding W. If alpha is optimal, then these two quantities will be the same. The difference between these two quantities is called duality gap, and there is a measure of whether the solution that we found is optimal or not. Again, this is not important to understand the model, but this is something that we will use in the laboratory to measure whether we found a good solution. We will learn the model in terms of alphas, and then we will use the duality gap to understand whether the model has converged to an optimal solution or not. Now this holds because our model, our original problem was convex. These are not general for any kind of optimization problem. The things that we say here hold because the problem that we have is convex. Another thing that we can say on the SVM solution is that for an SVM, for a primal dual, for a set of W, B, and alpha to be optimal, they must satisfy this set of conditions. This set of conditions essentially encode all the things that we have set up to now. And these are both sufficient and necessary conditions. Any optimal solution must satisfy this. Any set of W, B, and alpha which satisfies this is also optimal. What are these solutions? What we said before. The gradient with respect to W and B of the Lagrangian must be 0. The solution must be primal feasible, so it must be a W and B, a hyperplane, a plane that separates the classes with a margin of 1, and all the points must be outside of the margin region. The dual solution must be feasible. All the Lagrangian multiplier must be greater or equal than 0. And this is called also complementary slackness, if I remember right, condition. It tells us that the product of the alpha and the expression that represents the constraints for the point I must be 0. Remember what we said. One way to solve the problem is to require that the product of, that either the derivative of the Lagrangian with respect to alpha, which is exactly this, is 0, or the corresponding alpha is 0. Okay, we don't prove this. We take this for granted, but this, okay, we take this for granted. Now, this represents that it's optimal, that we are at a minimum of the at a stationary point of the Lagrangian with respect to W and B. These are feasible constraints. We know that this must hold because alpha I is the Lagrange multiplier and the solution must be feasible. The primal solution must also be feasible. This expression tells us something more. For this, we know that an optimal solution satisfies this, which means that for this to be 0, at least one of these two terms must be 0. Which means that for all samples for which alpha I is non-zero, is strictly greater than 0, then the corresponding Zi W transpose Xi plus B minus 1 must be 0. Let's remove the minus 1 and bring it outside. What does it represent? Where is this point located? If I have a point for which Zi times the score of the point is equal to plus 1, which point is it? W transpose Xi plus B. Let's imagine it's a red point. Where should I draw it? I can draw it in this region, I can draw it here, I can draw it here, I can draw it here, 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 and here. So let's call it 1, 2, 3, 4, 5, 6, and 7. Where should I draw it? It's a point that lies here, it's 6. W transpose Xi plus B equal to plus 1. Zi is 1. If it was from a blue point, it's a point that lies here. Which tells us that for an optimal solution, only the points that lies exactly on the margin can have an alpha I greater than 0. If a point is inside the margin, and of course it must be inside the correct side of the margin, it must be a feasible solution. So it must separate all the points correctly, and all the points must be either on the margin or outside. Then, for all points that are outside of the margin, not on the margin, but strictly outside of the margin region, the corresponding alpha I will be equal to 0. And the alpha I can be different from 0. It can also be 0. There are cases where both can be 0, but they are like kind of, you need to build them for that to happen. Typically, you can, but in general, this will not happen typically, but it doesn't really matter. All the points that can have an alpha that is greater than 0 must necessarily lie on the margin region. Why is this important? Because what is the first equation telling us? The optimal solution is a sum of the samples Xi in my training set. What are the weights of these samples? Are the Lagrange multiplier alpha I. But which alpha I will contribute to the sum? Only those that are strictly greater than 0. If I have an alpha I that is 0, the corresponding sample will not contribute to this sum. So this sum corresponds to what? The sum over samples for which alpha I is strictly greater than 0. But which are the samples that have alpha I strictly greater than 0? Where are they located? We said it a moment ago. Which are the points that can have alpha I greater than 0? Those for which this term is 0. Where are these points? Which points are these? We answered it a moment ago. The points on the boundaries of the margin. So the points that define the separation rules are those that are on the boundaries of the margin. These are the only points that they completely define W, and not only that, these are the only points for which alpha is greater than 0, and these are called super vector. This method is called super vector machine. The super vectors are those points that lie, we're still talking about a problem where the classes are perfectly separable, lie exactly on the margin boundaries for which the corresponding Lagrange multiplier can be greater than 0, and which affect the solution, and them and only them affect the solution. So once I have the supervectors, I can throw away all the other points, and I will still be able to compute my separation W. We can say something a bit more that we don't prove. Even before we know W, if we knew the supervector, we could throw away all the other points, and optimizing our model just using the supervector would find the same separation rule. That is, to find the supervector, we need to solve the problem. But if somebody comes and tells us which are the supervector, we can show that these supervectors are all and only the points that are required to find, not only to define, but even to find the separation rule. The separation rule will maximize the margin, but the margin will always depend only on the supervectors. So the supervectors are intrinsic of the data, not of just one iteration. If somebody tells us what are the supervectors for a specific data set, then we can throw away all the other points, and estimating and running the optimization problem on only those points will recover exactly the solution that we would have had if we kept all the points. Unfortunately, nobody tells us in advance the supervector, so we cannot use this trick to reduce the complexity of optimizing. But this tells us that the supervector are the points that define everything that there is to say about the separation rule in the supervector machine world. So, maximum margin for linearly separable classes. Finally, since W can be expressed in this way, how can we define the scoring function? Well, the Fourier function for a test point looks like I take the usual expression and then I will compare it with 0. If it's greater than 0, I will assign class +1. If it's lower than 0, I will assign class -1. Now, this is interesting because if I have the solutions in terms of Lagrange multiplier, the scoring function xt itself can be expressed how? As a sum over the training set of what? This transpose the test point plus b, but then I can bring the test point, the transpose inside, and then the test point inside as well, and I get the expression that I have here. I can see the scoring function as a linear combination of dot products between the test sample and training samples xi. The scoring function can be expressed, once I know alpha and b, as a function that does not require me to compute w, but can be obtained by simply computing dot products between xt and the training set points, and then using the same ways that defined the hyperplane. Notice that since this is a sum that contains alphas as weights, the only training point, only dot products that I need are actually the training points that are supervectors. So these I can make as a sum over supervectors only. So what I need are dot products between the test point and training supervectors. So I don't need dot products with all the training samples, I just need the product with the supervectors. Now, this, again, will come useful when we want to extend the model to nonlinear classification. Before we get to nonlinear classification, however, let's consider the case, let's extend the model to the problem where the classes are non-linearly separable. So now we have the same problem, but we can try as hard as we want. We will not find an hyperplane that correctly classifies all the points, which means since there is no hyperplane that correctly classifies all points, we can never satisfy this constraint for all the points, which means we will never be able to satisfy this as well. If we can't correctly classify all points with 1W, for sure we can't classify them with some margin within the two classes, which is harder than just classifying them correctly. So what we can try to do is try to figure out a way to solve this problem. We can imagine that we can try to do what? Figure out whether we can remove some samples. So whatever the plane we put, some points will violate our constraint. So we can intuitively say, okay, but then let's try to go back to the original problem. We can try to find a minimum set of points that we can remove, By removing those points, we can hope that the problem will be, again, a linearly separable problem. If we can find a few points that we can remove, and then the problem becomes, again, linearly separable, we can imagine that we may try to find a large margin between the remaining points, and know that the points that we removed are points that will be either misclassified or inside the margin. So we allow some points to violate the constraint that they must be outside of the margin region, and we will even allow them to be misclassified. We can imagine that what we want is to have few points that are misclassified and a large separation between most of the points that can be linearly classified. To measure this, we introduce for each point an additional variable that we call slack variable key. It's not an epsilon, these are key. Epsilon key. It's not an epsilon. Which we assume is greater or equal than 0 and represents how much a point is violating the constraint. So let's imagine I have a vector W and let's put, as usual, red points. Points here will not be violating the constraints because they are outside of the margin region. A point that is here is violating the constraint by a value ki. So it's inside the margin region by a value ki. So that means that point would satisfy the constraint if I allow the constraint to say that the point can be ki inside the margin region. So for all points, we replace the constraint with the fact that the points must be outside of the margin minus a possible value ki that represents the fact that some points may violate the margin. If ki is 0 for a point, then it means that it's outside of the margin. If this is strictly greater than 0, then it means that the point will typically be inside the margin region by a value ki. Remember that if I fix ki, then if I, okay, nothing, forget my last sentence. So ki represents how much I need to send a point inside for it to still satisfy my constraint. So I allow my points to be inside. I do this by saying, okay, I make my constraint less strict. If needed, I will violate it by this amount ki. I want to keep the points that violate the constraint as few as possible. We want to minimize the number of points that are inside the ki. So we want to minimize the points for which we need to ask ki to be greater than 0 to be able to still satisfy the corresponding constraint. Remember that if we could satisfy all constraints with ki equal to 0, that means the classes can be linearly separated. They can't, so we need to satisfy all constraints. Some ki will need to be greater than 0. We want to minimize the samples for which this happens. Now, to minimize the samples for which this happens is quite problematic, because we need to define a function that, given the values of the ki's, maps these values to the number of points for which ki is positive. And we would still need this function to be something we can differentiate, because otherwise it becomes difficult to work with that. One possible possibility is to consider the sum of the values ki to a exponentiated to a power sigma. If sigma is close to 0, then as soon as ki becomes larger than a small value epsilon, this value will become 1, which means that this, for a small enough sigma, is very close to the number of samples for which the ki is greater than 0. If sigma is close to 0 enough, then I need a very small value of ki for the ki to the power sigma to become equal to 1. So we can interpret this as a way, as an approximation of the number of points that are inside of the margin. And we can imagine that if we can remove these points, then we removed all the points that require Ki to be positive. The remaining points are linearly separable. So we can imagine that we can find an hyperplane for which on one side we want few points inside the margin, but we also want a large separation between the remaining points. Now these two are two competing strategies. Why? Because you can imagine that if I allow points to be inside the margin, even in the case of correctly linearly separable classes, if I don't allow any sample to be inside the margin, I may have that there are two samples of the classes that are closed, so I have a small margin. If I allow, let me delete this. If I allow some points inside of the margin, and then I imagine that I linearly separate the remaining points, I can imagine that if I allow these 2 points to be inside the margin, then the margin that I get with respect to the remaining points will be much larger. If I were to remove these 2 points, so I allow these points to be inside the margin, what I can obtain is a larger margin for the remaining samples. So on one side, I can increase the margin by allowing more points to be inside. That's like cheating. To enlarge the margin, I can ignore the points that would fall inside the margin. So to enlarge the margin, I can imagine that I throw away, I don't consider the points that are inside of the margin. But on one side, on the other, so this improves generalization. But on the other side, I don't want many points inside of the margin region. Many points inside of the margin may even lead to points which are misclassified. Or in any case, points that are inside the margin are closer to the decision rule, so it's easier that test points that behave similarly will be incorrectly classified. So on one side, I want few points inside the margin. On the other side, I want a large margin between all the points that I leave once I have accepted that some of them will be inside of the margin. These are two competing constraints. I can cast this as a single optimization by minimizing this expression where C is a hyperparameter that controls the trade-off between these two competing factors. Large value of C means that first of all, I want to minimize the number of points that I need to remove, and then large margin between the rest. Small value of C means that I can allow myself to remove many samples. The important thing is that the margin for the remaining ones is very large. So one is I want to generalize more, the other I want to make fewer errors on the training set, we can essentially say. That's still, again, the competing thing that we had with logistic regression. Small norm of W generalize, but also low loss reduce the number of errors that I make on the training set. Of course, this optimization is subject to the constraint that all points must respect the constraint eventually with a Ki that is greater than 0. This problem cannot be solved efficiently again. If I have very small value of sigma lower than 1, then this problem becomes difficult to handle mathematically. So what we do is we make the problem easier to reduce the complexity, the computational complexity of solving the problem by considering the smallest value of sigma for which we can still find an effective separation rule easily, which is sigma equal to 1. This results in the SVM primal objective for a generic dataset in this case, so we are not constrained to linearly separable classes anymore, where essentially our objective is a trade-off between minimizing the square norm of W and minimizing the sum of the key values. Remember that a large key values represents a point that is inside of the margin. The larger the key value, the more I am inside of the margin. So rather than minimizing the number of points, I minimize essentially an average. If you want, you can put a 1 over n here and divide everything by n. So again, if you want, you can see it as an average if you prefer. The average violation of the points So how much, on average, a point is inside the margin region. Again, this is a convex quadratic programming problem, so we can solve it fairly easily. It's interesting to observe that in this problem, the sum of the ki, we said, does not represent the number of errors. We said represents the sum of the displacement that I have. For example, for a solution where these are the classes, a hyperplane that looks like this, let's imagine it put the margin here, we'll have what? The ki will be the sum of this distance plus this distance plus this plus this plus these two for the red points. This is the sum of the ki. How much the points that are inside the margin or even the wrong side are from the correct margin they should be outside of. Now it's interesting to observe that while this does not represent a number of errors, we can show that this formulation behaves also as a way to reduce the number of misclassifications the model does. How? Because the sum of the ki is an upper bound on the number of misclassifications that the model does. Why is that? Again, let's consider points from the red class. This is the margin. This is the separation rule. This is the other margin. All points that are on the correct side will have a ki equal to 0. Points that are on the margin still have ki equal to 0. Points that are inside this side of the margin will have a ki that is greater than 0, but is also lower than 1. Ki equal to 1 will happen when the point lies on the separation rule. Remember this distance. If this is at a distance 1 from the separation rule, I need to eat all the 1 distance to go back to the separation rule. Remember, if a point satisfies this, for the point to be on the separation rule, this must become 0. So this must be equal to 1. Then if I have a red point on this side, which is the region margin but of the blue class, then this ki will be greater than 1. And here will be also greater than 2, but that's not the most important. That means that for misclassified points, ki will be greater than 1. So the sum of ki is greater or equal to the number of misclassified samples that I have. Actually, if what is on the hyperplane we say it correct, is actually strictly greater. But because every misclassified point will have a ki that is greater than 1. So you can imagine that points will have what? If they are on the correct size of the margin, so Zi, Si greater than 1, the ki will be 0. In their margin region, this red region, the ki will be between 0 and 1. In the blue margin region, it will become greater than 1, and then outside will become even larger. This is an upper bound of the number of errors. What is the number of errors function? The function that counts the number of errors is a function that does like this, the yellow one. If the point is correctly classified, it's 0. If the point is incorrectly classified, the value is 1. So for each point, ki acts as an upper bound of the function that counts whether that point is correctly or not misclassified. Which means that the objective function can be seen as a trade-off between large generalization and an upper bound on the number of errors. Having low second term here, if the second term is low, it means that I will also have low number of misclassified, because every misclassification will add at least a value of 1 to this of the second part of the objective. So we have again our two competing objectives, generalization and good performance on the training set. In this case, the generalization can be expressed explicitly to represent a margin between the two classes. Questions up to here? Okay, this is an example, yes. If C is very high, we want low number of errors, so we may overfit. It depends on how many data we have. If C is small, then we will typically underfit because we are ignoring the training set and we are just asking for a large margin. So we need to figure out a good value of C, like the lambda in the logistic regression. Typically, we use cross-validation to do this. Okay, now, as you can imagine, we had a Lagrangian formulation of the SVM problem, the original SVM problem. We have also a Lagrange formulation of the dual problem. This time, we need to add a constraint for each, a Lagrange multiplier for each constraint of the kind Zi W transpose Xi plus B greater or equal to 1 minus Ki, let's bring it inside, minus 1 plus Ki greater or equal than 0. And then we also have that the Ki's must be greater or equal than 0, so we have an additional set of Lagrange multiplier. Alpha is associated to this constraint, and the Lagrange multiplier mu I is associated to the constraint that this Ki must be greater or equal than 0. Now the primal variables are these three. We want to minimize the model, notice that we have it here, with respect to W, B, and the amount of displacement that I allow for my model. I want to minimize this expression in terms of W, B, and the value that measures how much a point is inside the margin. So these are all primal variables. Now, again, we can show that for a solution to be optimal, we have sufficient and necessary conditions that are given by these expressions. These represent the same thing as before. Derivative with respect to all primal variables is equal to 0. So with respect to W, with respect to B, and with respect to all the Ki's must be equal to 0. Again, this is important because it tells us the relationship between the primal W and dual solution alpha. Notice that what we are interested in is W and B. We don't really care about the values of the Ki. We minimize with respect to the Ki, but what we want to compute is W, the plane. So this tells us if we have a solution in terms of alpha, how it relates to a solution in terms of W. And the relationship is the same that we had before. Then we have primal feasibility, the same as before, but this time we allow that for some point, the points to be Ki inside the margin, and this Ki must be values that are greater or equal than 0. Either it's 0, the point is correctly outside of the margin, or I need to allow it to be inside the margin by some positive quantity. Lagrangian multiplier must be greater or equal than 0. And then these are the additional complementary slackness constraints that tell us which values are supervectors. In particular, we need to do one more step. First of all, the relationship between W and alpha is the same as before, and as before we have a constraint on the alpha that comes from the derivative with respect to B that looks the same as we had before. And then we have a relationship between the Lagrange multiplier alphas and the Lagrange multipliers mu I, which, given that mu I must be positive and alpha I must be positive, tells us also that the alpha I will be a value that is between 0 and C. As before, and I'm not doing the steps, we can replace these expressions and exploit this to define additional constraints that we need to understand which constraints we need to meet. I'm not going to prove that this is correct, but we can express the objective function in terms of just the alpha as the maximization of the dual objective that looks the same as the one that we had with the linear separable case. This is the same expression with the same constraints plus the additional constraints that the Lagrange multiplier in this case must be lower or equal than C. This is equal to the SVM that we have seen before, which is also called hard margin. Hard margin because we did not allow any points inside of the margin. SVM, this we are seeing now is called soft margin because we allow some points inside of the margin. From the dual point of view, the solutions are, the problems are equivalent, except that in the hard margin, we just require the supervector, the alpha values to be greater than zero, greater or equal than zero. In the soft margin, there is also an upper bound on the values of the alpha, the Lagrange multipliers, which combined with this tell us that if alpha I, for this to be zero, either alpha I is zero or the corresponding values inside is zero. But if alpha I is different from zero, if alpha I is different from zero, that means that this term, Zi, W transpose Xi plus B minus 1 plus Ki must be zero. Now, before, we didn't have the Ki that told us that the supervectors are the points on the margin. Now we have the Ki, so we need to understand what happens. Alpha I different from zero, we have two options. Alpha I is still lower than C, of alpha I is equal to C. When alpha I is lower than C, then mu I is greater than zero. If I is strictly lower than C, mu I must be strictly greater than zero. Complementary slackness on the Ki, if mu I is greater than zero, if mu I is greater than zero, Ki is zero. So if I have alpha I strictly between 0 and C, then Ki will be 0 and Z transpose W transpose Xi plus B will be equal to 1. These are supervectors that correspond to supervectors that lie exactly on the boundary of the margin as before. But now we have an additional kind of supervector when alpha I is equal to C. When alpha I is equal to C, I can satisfy, then I can have mu I is equal to 0, which means that these constraints can be satisfied by any Ki that is greater or equal than 0, which means that if alpha I is greater than C, then this constraint, for this constraint to be satisfied, either Ki can be 0, then the point is still on the margin, or Ki is greater than 0, which means that the point is inside the margin. So essentially now we have a situation like this. Points that are correctly classified, alpha I, and outside of the margin is 0. Then as I move on the boundary of the margin, here my alpha I will increase, will become greater than 0 and lower, or I can say lower or equal to be precise, lower or equal than C. Then once I have a point that is inside, the corresponding alpha I will be equal to C. This is called bound supervector because it reaches the bound for the values of alpha. So we have two kinds of supervectors. We have, I don't have the picture here, I have the picture here. Supervectors that are the purple one, they behave like those that we had seen before, and a new kind of supervectors that are inside the margin. And notice that for this to hold, we can say the opposite. Where is it? For this to hold, if Ki is greater than 0, then the corresponding C alpha I must be C, which that tells us that the opposite is also true. All points that are inside of the margin or misclassified are supervectors. So the supervectors are all the points that are on the margin, and when I say on the margin and all, there may actually be points on the margin that are not supervector. Again, this is something that mathematically can happen, but in practice it's difficult, but it can happen. But in any case, there will be supervectors on the margin, and then all the points that are inside the margin region or wrongly classified are the supervectors. And those points are all and only the points that define my separation rule. So again, the hyperplane W depends only on the super vectors. And again, when I optimize my problem, I have again, I can solve the problem by solving the dual formulation in terms of the Lagrange multipliers alpha, and then recover the primal solution. I can also recover the B, but since we are not going to do it in practice, we will not say how it's done. What's important here, and in the laboratory we see a problem where we don't have B, so we will not have this constraint, and we will not have this, which simplifies greatly the complexity, the computational complexity of the problem. Again, the problem depends only on dot products between training points. And the score, once they're computed alphas, can be expressed as a sum over super vectors, those values for which alpha is greater than 0, between the test point and the training set points, or in particular between the test points and the super vectors. Now, how do we solve the problem? To solve the SVM problem, we can use numerical solvers. If we are interested just in the primal formulation because we are interested only in a linear model, then we can directly forget all about the dual solution and focus on solving just the primal formulation. Now, for the primal formulation, we can give a new expression that essentially represents what I said before. What did I say before? When I have a point in the primal formulation, I will have what? Points that are correctly classified will have a Ki that is equal to 0. Points that are inside of the margin will have a Ki that goes from 0 to 1 in this way, and then it still increases linearly. And then what I have is a sum of these Ki's for the samples. This is the loss term of the objective, this part here. Now we can observe that this function corresponds to what? Well, it's a function whose value is 0 whenever Ki is greater than 1, and Ki whenever Ki is lower than 1, which we can represent as max between 0 and 1. Sorry, this is not Ki, it's 1 minus Ki when Ki is lower than 1, which we can represent as maximum between 1 and minus Ki. Now, since Ki is equal to this quantity, because Ki is equal to, because when my point is violating a constraint by Ki, it means that this is true. So from this I can recover that Ki is 1 minus this term, and sorry, I forgot the Zi. Then the objective function can be written in this way. I can solve my problem by optimizing this objective, and now I can throw away my constraints because the constraints have been absorbed in the fact that I already saw how the constraints affect the value of the Ki. So this objective function here, the optimal of this objective unconstrained function will correspond to the optimal of this constrained optimization problem. This means it does exactly the same. It says, let's find W and B which have a large margin, but for points for which this term is greater than 1, I will have a cost 0, which corresponds to the original SVM. For points for which this term is lower than 0, so points for which this term is lower than 1, I will have a cost that increases linearly in this way. This is exactly what we had with the original SVM. This function here, max between 0 and 1 minus, let's call y, is called also inch loss. It's a function that corresponds to a cost that I will pay because I can misclassify my points. So we can cast the SVM objective. How? Let me see if I have a plot here. Yes. I have a minimization of a square norm of W plus C times a sum of values, each computed on a sample, so sum of a loss term. This time the loss is the hinge loss. Each of these terms represents a cost that I pay if I use WMB to classify the points. If, let's put here ZI, SI. If a point is correctly classified and let's look at the sum of the losses, the hinge loss. So 1 minus ZI, SI plus. If the point is correctly classified, I will pay a cost of 0 if it's correctly classified and outside of the margin. If it's inside the margin region, so as before, ZI, SI. If ZI, SI is greater than 1, the point is correctly classified and outside the margin, I pay 0. If I reach the margin boundary, I'm here, and then as I move in the wrong direction, I pay a cost that increases linearly with how far I move from the correct margin boundary, the boundary on the side of the correct class. This looks similar to the logistic regression loss. The logistic regression loss was what? Was this. But now, let's take this expression, divide everything by Cn, and multiply by lambda, since C is a factor that we need to estimate by cross-validation. We can alternatively rewrite the objective function as a function of lambda, which can depend on C or not. We will need to estimate it in any case. And rewrite the SVM objective function in this way, it looks exactly like the regularized logistic regression model, just with a loss that now the hinge is the hinge loss rather than the logistic loss. And how do the two losses compare? They compare like this. Logistic loss, exponentially decreasing cost, but I still pay a cost also for correctly classified samples. Linearly increasing cost on the left. SVM, I pay a cost that increases linearly for all points that are not just misclassified, but also for points that are misclassified, I have a cost that is 1 or greater and increases linearly. But I also have a cost for points that are inside the margin region. If a point is correctly classified and outside of the margin region, I don't pay anything. The cost becomes 0. So the two costs are fairly similar. They differ in how they penalize points in this region, but asymptotically, they both go to 0 here and grow linearly in this side. Of course, they behave differently because they are not exactly the same. The SVM does not penalize anything that is correctly classified. The logistic regression cares about how well it's classified, even for points that are very far from the separation rule. We still have a cost that never becomes 0. SVM, once we are outside of the margin region, how far we are outside of the margin region becomes irrelevant. Questions up to here? Of course, the amount of regularization affects the boundary that we can obtain. We have a trade-off between the two objectives, large margin and low number of errors. Here we have a large value of C, so we try to minimize the amount of errors, and then the margin is small. You can see that the margin is small. These are the values equal to +3 and -3, so the margin region essentially would correspond to this region in space. This is the margin. With a smaller value of C, you can see there are many more points inside the margin region. All the diamonds are supervectors, so they are either misclassified or inside the margin, except very few that are exactly on the boundary. But they are very few compared to the total. In this case, the margin is much larger, but I have many more points that are not outside of the margin. For the SVM, being really correct means not just being correctly classified, but being correctly classified and outside of the margin. So these are points on which I'm paying a cost because they are inside the margin region. And these two compete. To have a larger margin means that if I don't consider this point, I have a large margin between all the rest, but here I am paying a cost also for these points. which one do I prefer? Well, cross-validation helps me to define whether these solutions will be better. Large margin means I will generalize better, but may generalize better at higher cost, which means that I will do worse on the evaluation set because I generalize better a worse classifier. Low norm of W, high norm of W means small margin. Small margin may mean much better classification on the training set, but lower generalization to data that is not exactly those that I have seen. Which one should I choose? Again, typically we will need to use cross-validation to decide between these two. Okay, now let me say a couple of words on how to make the problem non-linear, then we will have enough for the laboratory, and then I will finish what remains afterwards next week. But to do the laboratory, this will be enough. We have two ways to solve the problem. Solve the prime for the moment. For a linear model, we can solve the primal or the dual. The primal, we minimize this objective function. We finally found a way to express it without constraints with respect to W and B. The dual, we maximize this expression subject to these constraints. For any feasible solution, the difference between the two objectives is duality gap, and it will be zero if a solution is primal and dual optimal. Characteristics of the problem. Here, the complexity depends on the size of the input features. And scoring is simply a dot product between W and X, so it also depends on the size of the input features. The dual, the complexity depends on the number of samples in my dataset. The number of Lagrange multipliers is 1 per sample, so the complexity is not related directly to the dimensionality of the feature, but to the number of the features. So typically we already see that this will be easier to implement if I have few points of large dimensionality. It is typically where I want to use a large margin solution. Remember that large margin is used to generalize better. So if I have large dimensional samples and not many samples, then a large margin solution is something that typically I want to may be good for my problem. Scoring complexity has a complexity that depends on the number of support vectors, if I express it in the dual. So why should I use the dual? Well, if I have few samples with respect to the dimensionality and I want to leverage the SVM exactly because the maximum margin may generalize well to unseen data, or other case, when I want to apply a nonlinear transformation. To perform nonlinear classification, what we can do? Well, one possibility is to do the same as we did for logistic regression. Rather than training a linear model in the samples, we compute a nonlinear expansion of the samples, and then we train a linear model in the expanded features, exactly the same as logistic regression. We expand with our quadratic expansion, then we use those as features, and we train a linear SVM with those quadratic expanded features. This will give us exactly a quadratic separation surface. However, this depends on the dimensionality of the feature expansion. Because the model depends on the dimensionality of the input features of the model. In this case, the input feature of the models are the transformed features. Same problem as logistic regression. Quadratic logistic regression, as we casted it, requires that we build a quadratic expansion of our vectors, which has a complexity d to the power 2. Here, the dual model depends only on dot products in the expanded of the feature. We've seen that for training, we need to compute this kind of products. For test, we need to compute this kind of products, which means that if we introduce a nonlinear expansion, the things that we need are the products between the expanded training set features and the products between expanded supervectors and expanded test vectors. That's all we need to represent the model. Now, this may seem like not being much, because if I were to compute it like this, you would say, okay, but where do I gain? If I compute phi and I compute the dot product, if the expansion requires d squared elements, here I need to compute d squared elements and then a dot product between two vectors that are of size d squared. Now, the good thing comes from the fact that in many cases, we can represent with those products without computing phi at all. So we can compute those products in an expanded feature space in a way that does not depend on the complexity on the size of the expanded features. If this is true, and let's see in a moment, let's just see why with an example, then we will go back. Consider, for example, our quadratic feature expansion. Our quadratic feature expansion does, if I have x1 and x2, I will have vec of x1 transpose. And now let's use a different expression where I put a square root here. It doesn't change the expansion, but simplifies the way the final expression, the form of the final expression. This is still a quadratic expansion of the feature vector. I just rescaled the input value here. I want to compute this vector transpose vec of x2 transpose, square root of x2 and 1. Now this we can show it's x1 transpose as a matrix x2 transpose plus 2x1 transpose x2 plus 1. This term, which is the matrix, the same operation but represented in terms of matrix. Remember, if I have matrix A and B, vec of A transpose vec of B is equal to the scalar product between the two matrices A and B, is equal to what? I can represent it as, and here I need to use some tricks, as trace of x1 transpose x2 transpose, which is equal to trace of x1 transpose x1 transpose x2. These are two numbers. It's equal to x1 transpose x2 to the square. And then you see that I have x1 transpose x2 to the square plus 2 x1 transpose x2 plus 1, which is equal to this to the square. Which means that the product phi of x1 transpose phi of x2 can be computed without ever computing phi. I can compute it in this way. This way is a complexity that is not d squared. The complexity of this is still d, the original feature complexity. So since I don't need the full vector but just the dot products, it's possible for some feature expansions to find a way to compute the dot products between expanded features without actually computing the expansion in an efficient way. This is called a kernel function, a function that given x1, x2 computes the dot product in the expanded feature space, but typically without computing the expansion at all. Notice that if I have this kernel function, then during training my matrix H depends on these terms, so I can replace this term with a call to the kernel function between training set points. At test time, I need to compute the products between expanded training supervectors and expanded test vectors. Again, this corresponds to kernel functions between the training set point and the test set point. But this kernel function computes these products in an efficient way that is not necessary, does not has necessarily the same complexity as building the full expansion. For example, for the quadratic expansion, we have the quadratic kernel that computes the dot product between these quadratic expansions of my data that corresponds to this expression. This expression has a complexity that is linear in the size of the input space. And we can generalize. We can show that we can build polynomial kernel function that represents dot products between degree d polynomial expansion of our features by simply taking the dot product between 2 points to the power d. Doing this corresponds to computing the dot product between two expanded vectors, where these expansions are degree 4 expansions of the inputs. So they would correspond to degree 4 polynomial surfaces. Remember that if I were to compute the expansion, then this would be the equation that defines a separation boundary. If this is a term that contains the elements of x to the power 4, this is a 4th degree function in the input space. So if I want to compute a 4th degree separation function, I would need to have an expansion phi that contains, let's say that I have vector xi with components x1 through xm. I would have to have x1 to the square, x1 to the power 4, x2 to the power 4, then x1 to the power 3, x2, x1 to the power 3, x3, x1 to the power 3, etc. So all 4 or power of degree 4 that I can make out of the original elements, and then the degree 2 elements, and the degree 3 elements, degree 2 elements, and so on. For the quadratic expansion, I had exactly this. These terms here, if my vector contains components x1, x2, and x3, we'll have x1 squared, x2 squared, x3 squared, x1, x2, x1, x3, and so on. Here I would have the term x1, x2, and x3 with some coefficient, and then I would have 1. This is a quadratic expansion which corresponds to quadratic separation rule. A degree d expansion here would have a complexity that is equal to the original input space to the power d, but the kernel function has a complexity that is still linear in the original size of the feature space. By using this kind of kernel function to compute my dot products, I can train a model whose separation rules are quadratic separation surfaces. And the complexity, the computational complexity of the kernel is the same as the polynomial of degree 2. And actually, I can generalize to any degree d. Just a matter of changing the value d here when I compute dot products to build my matrix H. At training time, I need to compute matrix H. And once I solve my problem in terms of alpha, for a test point, I need to compute these kernel values here. So I can use this model to implement nonlinear separation through embedding in an expanded feature space, but without computing explicitly the embedding, because I can represent the dot products in the expanded feature space in a compact way. Now, a question is, which kind of function k I can use as kernel function? Trivially, if we have a function phi that does the expansion, a naive kernel function is just a function that computes explicitly the expanded features and the product. Typically, this is not very interesting because it's maybe expensive to compute, but this shows that for any feature expansion, we can devise at least one equivalent kernel function. Maybe not efficient, but it exists. If we have a feature expansion, then we have a kernel function k. Then typically we would like to have kernel function that compute the same thing, but in an efficient way. But that's a different question. Then we can ask the opposite. Which functions of two variables corresponds to a mapping phi? And can we do a mapping that is general enough that it allows us to obtain more complex decision boundaries? Well, to answer to the first question, we can devise a way to verify whether a kernel function is, whether a function is a kernel function, but typically these are not practical to use. So the answer is, there are some rules that we can use to verify whether a function is actually a kernel function or not. It identifies these are sufficient conditions, these are not necessary. There may be functions that do not satisfy these conditions, but still are valid kernels, and then we can't apply this approach. But in any case, even for function that satisfies these conditions, typically this is not a useful way to find how to build kernels. So how to find useful function? So typically, the way we identify useful kernels is to use either well-known kernels or rules to combine kernels that guarantee that the combination is valid. For example, if I have a kernel function between two vectors and another kernel function between two vectors, the sum of these two is still a kernel function. This corresponds to a feature expansion phi, let's call it A and B. Phi A of X, this corresponds to a kernel expansion phi B of X. The sum of these two corresponds to an expansion that is phi A of X stacked with phi B of X. So we can see that we know that these are kernels, so they correspond to an expansion. We know that we can stack the expansion. If we stack the expansion and try to compute the corresponding kernel, we can see that it can be represented as a sum of the original kernels. So there are rules. Typically, we will restrict to kernels that are well known. For us, well known will be the polynomial one that we just discussed, and another kernel that is called radial basis function kernel. It is a kernel that is general enough in the sense that it allows us to obtain decision rules that can grow arbitrarily complex as we increase the size of the data set, of the training set. So the complexity will increase with the complexity of the training set. Now, the radial basis function have a kernel that has this form. It's called radial because it depends. The kernel, remember, is the dot product between two expanded features. It depends, it's called radial because it depends only on the distance between the original points in the input space. And radial because it depends just on the distance and not on the location or the directions in which these points are located. And it's called Gaussian because the expression resembles that of a Gaussian density. It's the exponential of minus gamma, where gamma is positive, the square distance of x1 and x2. Here you see some examples of this model. Again, the more I regularize, the more complex, the more I weight the higher C, the less I regularize, so the more complex my decision rule, the lower the value of C, the more smooth my decision rule are, because I tend to favor generalization, which we can also say generalization corresponds to the decision rules that are typically smoother. They change less sharply because the sharp changes are typically related to overfitting. And what are these Gaussian radial basis functions representing? Well, to understand how they work, we need to understand what the kernel represents. Here you can see some example where you can see that I can obtain very complex decision regions. Why? Well, the kernel, as we said, depends on the distance between points. Points that are similar, we have, so points that in the original space are close, will have a large kernel value. If two points are close in the original space, the kernel value is exponential of minus gamma, the square distance between the points. The kernel value is between 0, so between 0 and 1. It will be close to 1 when the points are close. If I take 2 points that are far, then the kernel will be close to 0. Now, gamma, we see that gamma controls the trade-off when I say points are close and points are distant. But imagine that for some gamma, there are points that are close and points that are far. Points that are close are those for which the kernel is close to 1, because this distance is close to 0. So exponential becomes exponential of 0, 1. Points which are far, this value is large, exponential of minus a large number becomes 0. And then I will go back to this slide. It's not here. Okay, this is not in the slide, but it doesn't matter. How does this affect the decision rule? Remember that my decision rule, my decision boundary is the score for a test point, which is the sum of alpha I, zi, kernel between xt and xi plus a bias. This equal to 0 defines the separation rule, the solid line that you see here. So the separation rule is controlled by the supervector. And how? Well, let's consider only the bound supervectors. We know that most of the supervectors have alpha I equal to C. Some of them will have an alpha I that is lower, those that are exactly on the boundary, but most of them will have a value equal to C. So for simplicity, let's consider only them. If all the supervectors have a value C, I can bring this outside. And again, let's imagine we have a model with a bias 0 because the bias does not influence what I'm saying. Which means that if I can bring the C outside, I can remove it from the equation because I simplify, then my decision boundary is defined by sum over I of Zi kernel between xt and xi equal to 0. If this is greater than 0, we'll assign class 1. If this is lower than 0, we'll assign class 0. But the kernel is what? If 2 points are close, the kernel is 1. If 2 points are far, the kernel is 0. So if I have a, let's imagine these are supervectors and I have a test point. These are supervectors from the two classes. For a test point, the points that are close to the test point will have a kernel value that is close to 1. Those that are far will have a kernel value that are close to 0. So I can say that if gamma is sufficiently, well, if I can imagine that the sample that are close will have a value close to 0, not close to 1, not exactly 1, while the other close to 0, not exactly 0. But again, let's make a simplification. It means that essentially what controls the value of this score are the samples, the supervectors that are close to the test point. How? Each supervector will contribute with a value that is the kernel time its label. So again, for simplicity, imagine that the closed supervector have a kernel that is, for all of them is close to +1, so they are all more or less similar. Then, if my test point is close to supervectors that are mainly from the red class, my score will be positive. If a point is close to supervectors that are mainly for the blue class, the score will become negative. Which means that essentially, as a first approximation, we can see that this expression behaves how? A point will tend to have a label that corresponds in a soft way, in a very soft way, to the labels of the majority of the points that are close to that one. Actually, we can even show it more. We can show that if we take very large value of gamma, the model becomes equivalent to the one nearest neighbor. The score of a point will be the label, will be the score equal to the label of the points that is closest to that one in the training set. Now, this gamma controls how much we have that the kernel goes from 1 to 0 as we move away from a point. So if gamma is small, then for most points of the training set will be close to our test point, which means that our solutions will be smooth. If I move by a bit my test point, the points that are still considered close will still be the majority of the points in the training set. So my labels, my scores will change softly. I need to move a lot to change the kernel values of my test point and the training supervectors. If gamma is, sorry, it's this picture, not this picture, but it's the same. It's this picture here. Smooth separation rules. If gamma is large, then as I move a bit, my kernel will change quickly. So the points that are close to that are considered close to my test point will change quickly, which means that my decision rules will change much more sharply. As I move, we essentially will consider only very close point to a test point to decide the label of that point. We call this a narrow kernel. This is a large kernel. The large kernel will result in surfaces that are much more smooth. Narrow kernel will result in surfaces that are much more sharp. Typically, This is better if I have enough training data to estimate a complex separation rule. This will be better if I have fewer training data. Having a small value of gamma brings me solutions that are simpler, that are more smooth. And then the rest we will see next time.